You've probably been hearing a lot about Formula One in the last couple of years as the sport's popularity has exploded due to the Netflix show Drive to Survive, more sponsors getting involved in the sport, more tracks in the US being added like Miami and Las Vegas, and honestly with just drivers, F1 itself, and teams becoming more active on social media. But what is Formula One? Well, Formula One is the pinnacle of motorsport, where the fastest cars in the world race around tracks all around the world at mind-blowing speeds. These cars can hit 220 miles per hour in straights, and that's not even the most impressive part. It's the speeds they can take corners at that makes this sport really stand out. But how do they do it? Well, Formula One is more than just about speed. It's about science. Each one of these cars on the grid is a finely tuned engineering and physics science project on wheels, and in this video, I'm going to break down some of the science behind these cars, including the G-forces that the drivers feel, drag that the cars experience, and the downforce that these cars generate both from their wings and from their body that allows them to take these turns at these amazing speeds. So let's get into the physics of F1 cars. So first, let's talk about the speed of these cars. On a straight, full out, these cars can go 220 miles an hour. That's 350 kilometers an hour. To give you an idea of how fast 220 miles an hour is, the human reaction time, on average, is about 250 milliseconds. If you're driving one of these cars at full speed, in 250 milliseconds, you will cover 25 meters. So what that means is if you're driving in a Formula One car at full speed and a deer jumps out at you 25 meters in front of you, you will actually hit that deer before your brain can even process that the deer is there and send a signal to your brain to apply the brakes or to turn the wheel. But F1 cars don't just go fast in a straight line. It's really the cornering speeds that make these machines amazing. Some corners, like turn 16 in Spa in Belgium, they can take at 200 miles an hour, and they can take hairpin turns, like turn 7 at Imola in Italy, at 100 kilometers an hour. That's how fast you go on a highway. And taking these turns is not easy on the drivers. Drivers can experience upwards of 6 Gs on some of these turns. But what are G-forces? Well, G-force stands for gravitational force, or the force of gravity. And it's kind of a way to think about how strong gravity is pulling you down. So right now, sitting in your chair, you're experiencing 1 G pulling you down. That's just the regular force of gravity pulling you down. But you've likely been in a situation where you've experienced more than 1 G pulling you down. Think of getting into an elevator, and as soon as that elevator starts accelerating upwards, you feel heavier for like a fraction of a second. That's you experiencing more than 1 G pulling you down. And so the more G forces you're experiencing, the heavier you'll feel. So let's say we can crank up Earth's gravity to 2 Gs. You would feel twice as heavy as you are. Or if we could crank it up to 6 Gs, you would feel 6 times heavier than you are. These Formula One drivers experience these G-forces, but instead of experiencing them downwards, they're experiencing them sideways. And so when they turn the wheel and they get pushed to the side of the car, they're being pushed with a force that's 6 times their weight. And so their necks have to be very strong to withstand those forces. You'll see that Formula One drivers tend to have really thick necks. Not only that, they exercise their necks. They'll strap on a contraption to their head, and their head will be pulled to one direction, and they have to kind of resist it with their neck muscles and on both sides. They actually have to practice and train their neck because they're experiencing these immense G-forces when they're taking these turns. But why are these cars able to take these turns at such speeds that cause these drivers to experience these immense G-forces? Well, the answer is downforce. So the speed that you can take a corner at in your car really depends on how much grip you have between the tires and the ground. And Formula One cars use downforce to amplify their grip on the road. Now, grip on the road is really just the force of friction between the tires and the ground. And force of friction is determined by 2 things. The relationship between the 2 materials in contact, so in this case, tire compound and tarmac, and the weight of the car, really how much force is pushing the car into the ground. And so Formula One engineers can increase the effective weight of the car by adding downforce, pushing the car into the ground, increasing the force of friction between the tires and the ground, increasing the grip, and therefore allowing the cars to take much sharper turns and much faster speeds. But how do they generate this downforce? Well, there's 2 ways. I'm going to use my little model F1 car here made from Legos to demonstrate that. There's 2 kind of key factors, key parts of this car that are generating the downforce. There's the 2 wings. There's the front wing and the back wing that are generating a lot of downforce, but this also generates a lot of drag, which I'll talk about in a minute. But also the floor, the body of the F1 car, generates actually probably the majority of the downforce. Now, both of these wings work in the same way, but it's easier to visualize with the back wing, so I'll talk about the back wing. The back wing generates downforce using two principles, Newton's third law and the Bernoulli principle. So Newton's third law says that for every force, there's an equal and opposite force that acts in the opposite direction. So if object A pushes on object B will push back on object A with the same force. So if I'm pushing on a fridge, the fridge pushes back on me with the same force. That's why when you're wearing ice skates and you push off a wall on ice, you slide backwards. So if you imagine the air streaming across this F1 car, when it gets to this back wing, you can see that there's an elevation to this wing. It's angled up, and that sends the air upwards. So the air has been pushed, accelerated upwards. So that means that this wing is imparting a force on the air to push it upwards. And that means that the air must then, by Newton's third law, push back down on the wing. For every force, there's an equal and opposite force. The wing pushes the air up, the air pushes the wing down. That's generating some downforce. That's one way. Now the other way is actually that this wing works just like an airplane wing, but upside down. So an airplane wing shape is called an airfoil, and it's designed so that in an airplane, the air that goes above the airfoil is traveling at a faster speed than the air that goes below the airfoil. And Bernoulli's principle tells us that faster moving air is at a lower pressure. And so on an airplane, when you have air going above an airfoil at faster speed, it's at a lower pressure than the air going under the airfoil at a slower speed at a higher pressure. Now pressure is just force per unit area. And so under the airplane wing, the higher pressure means that there's more force per unit area pushing up than above the wing where there's low pressure. There's less force per unit area pushing down. Therefore, the net overall force, or the net overall pressure, is pushing upwards. And so the airplane gets pushed upwards. We call that lift. The force that's acting as a result of the pressure differential on a wing is called lift. There is actually a really cool demonstration you can try yourself to prove that Bernoulli's principle is true. Give me a second. So if you take a little piece of paper like this and you put it at your mouth, below your mouth, and you blow forwards, you're actually generating faster moving air above the paper than would be moving below the paper. And so if Bernoulli's principle is true, that would mean that there's a lower pressure air above the paper, higher pressure air below the paper, and so that higher pressure air should push the paper upwards. So the paper should rise when you blow past it. So let's see if it's true. It worked, right? Because we're generating faster moving air, which is lower pressure, which is causing that paper to move up. Now, a Formula One wing works just like an airplane wing in the exact same way, except it's upside down. The air passing above the wing is actually slower than the air passing below the wing, and so there's a higher pressure above, a lower pressure below, and so the wing gets pushed down. So the angle of the wing actually matters. The steeper the angle, the more directly upwards that air will be pushed, and so the greater the downforce pushing down, to an extent. Now, the problem with that, though, is that the more you increase the angle of the wing, the more drag you have. Drag is force acting backwards against the Formula One car, so it's acting in this direction, and it's actually slowing the car down. In fact, there's something called a drag reduction system, which is where they can open up their back wing, but we'll get to that afterwards. So with the Formula One wing, you can generate downforce to an extent, because at one point, you start generating too much drag, and you're slowing the car down more. Okay, so that's how a Formula One car generates downforce using the wings. But how does it generate downforce using the floor? Well, to understand that, you have to understand something called the Venturi effect and Venturi tunnels. A Venturi tunnel is a tunnel that has two thicker sections separated by a thinner section in between. And when fluid flows from one thicker section through the thinner section into the thicker section, it speeds up through that thinner section. And Bernoulli's principle tells us that faster moving fluids are at a lower pressure. And so a fluid moving through the middle section of a Venturi tunnel is moving at a faster speed and lower pressure than the either side of the Venturi tunnel. And so if F1 engineers can design the floor of an F1 car to be the shape of a Venturi tunnel and generate a lower pressure here in the middle section compared to the high pressure air up here, then the car will effectively be pushed down, and that's exactly what they did. F1 engineers have designed, now you can't see it on this F1 car because it's just a model, but on either side of where the driver sits, there's a Venturi tunnel here and here. And so on an F1 car, on the floor, there's a thicker section here that tapers to a thin section and to a thicker section here kind of between these wheels that we call the diffuser. And so effectively, they've made two Venturi tunnels on the bottom of this F1 car. And so you have really fast moving low pressure air here compared to the higher pressure air above. And so again, it just pushes the car down just like the wing does, just like the Bernoulli principle on the wing. So this entire F1 car is kind of like a wing upside down with air pushing it down because of the lower pressure below the car. But just how much downforce do these F1 cars produce? It's actually wild. At about 100 miles per hour, an F1 car is generating as much downforce as its weight, essentially doubling its weight. But at max speed, 220 miles per hour and above, an F1 car can actually generate 2 to 3 times its own weight in downforce. That means that theoretically, driving at maximum speed, an F1 car could actually drive upside down on the ceiling. Because in this orientation, the F1 car is generating downforce up, fighting against gravity. And so if this thing was driving at max speed, then it would be generating more force upwards than the gravity pulling it downwards, and it would actually stick to the ceiling due to its own downforce. So I briefly mentioned that these wings can generate drag, or actually do generate drag. And the problem with drag is that it slows these cars down in straight lines. And so modern F1 cars have something called a drag reduction system that in specific areas of a track, drivers can push a button called the DRS button on their steering wheel that will open up their flap just like this. So it stops generating drag and has an open area that air can flow through. That gives them something like 12 kilometers per hour more speed in the straights, which is really exciting because it allows for overtakes to happen a lot more often. The reason that I love watching Formula One so much is not just with the fast cars, the exciting races, and the stories of the drivers and the teams, but it's that it's just a big science project where teams of engineers are trying to make the best car possible under the strict FIA regulations, and they're trying to extract fractions of a second out of these cars. So if you watch a race weekend, on Saturdays is usually qualifying, where drivers will take their car and push it to the limits around the track and set the fastest lap time possible, which sets the starting grid for the Sunday race. The qualifying times, the top 10 drivers, are usually within a second of each other, like tenths of a second, hundredths of a second separating first and eighth. In fact, there's been times where drivers have qualified with the exact same time to the thousandth of a second. And so if teams can extract even fractions of a second more through aerodynamic properties or material properties of their car, that could be the difference between first place and sixth place. There's so much more amazing physics and engineering in these cars. And if you want me to make more videos, if you like this one, hit that like button, hit the subscribe button, hit the bell, do all the things, share the video, and thank you so much for watching. I'll see you in the next one. Stay curious. Bye, everybody.